Hello everybody. One of the topics in machine learning and in clustering data is Gaussian Mixture Models, or GMM, which has some similarities and some differences to the k-means clustering. So k-means clustering, as you know, when it clusters the data into different groups, it does not account for the variances of those clusters. But the Gaussian mixture model, as we'll see, it does account for the variance, and basically it will give you several Gaussian distributions, okay, and assigns each data to one of them using a probability, not using a 0 and 1. That's another difference it has from the k-means clustering. And each one of those clusters has a center, a mean, it has some variance, and it has some proportions. Okay, so it's really kind of parametric clustering. It gives you some parameters, right? All you need to give it is the number of clusters, just like k-means, but k-means, all it gives you back is the center of each cluster and a label whether your data belongs to any of the clusters or not, okay? But here you have more than that. Not only you have center, it gives you the variance, it gives you the proportions, which is the relations between the number of the data in each cluster to the total number of data, and of course a label, but this label is not a hard 0 or 1. It's a probability that each data belongs to each one of the classes. It's a number between 0 and 1. So it's basically, I would say, a more complex method of clustering compared to k-means. So here you can see some examples, right? Here I have some clusters here, some clusters there, and you clearly see that the covariance matrices are different. Here you have diagonal covariance matrices, so the distribution looks kind of like a circle from the top. Here they are not the same, so it looks basically elliptic. You know, in general, a multivariate Gaussian distribution function looks like this, where mu is the vector of the center and sigma is the covariance matrix, right? So this is the kind of function that we have, and we're going to use in formulation for GMM. So now we can say that the total probability of any data point x in the GMM comes from a summation of some normal distributions, right, where this ni is the ith normal distribution with the average of mu I and covariance matrix of sigma I, and x, assuming that it is coming from that is a probability distribution. And each one of these normal distributions is multiplied by its own proportions, pi I, and sum it up all together, you get the total probability distribution for what? For the observation x. Okay, and this pi i's is to show that the number of samples in each one of these clusters is not the same, okay? So these are proportions, like basically the number of samples over the total number. So if you add all of these pi's together, summation of all of these pi's, these proportions, is equal to 1. Okay, so each one of them is a fraction. Now, to formulate this GMM, here we're going to use expectation maximization, maximum likelihood, basically. But here I need to introduce a binary random variable z that has k entries, and only one out of these k entries is 1. All of the others are 0. Remember, we had a topic in one of my previous videos called one hot encoding, so this is kind of like that, right? One of them is 1, the others are 0. So the z variable is such a thing, and then if we do that, now which one of them is 1? Remember, we said out of the k entries, only one of them is 1. Which one? The one that the data belongs to. So basically this z variable is kind of like a label showing which one of your clusters the data belongs to. Okay, so if the entry 1 of it is 0, it means it belongs to cluster 1. If it's 2, it belongs to cluster 2, and so on. And in general, you have k entries because you assume you have what? K clusters. So this capital K is what? The hyperparameter, which is the number of clusters that you give to the GMM algorithm. So this K is determined by you, not by somebody else. And again, it's not by the machine learning algorithm, and it's a hyperparameter. Okay, so it's one of the things that you need to be giving to the algorithm. Now, here I can say that the chance for the kth entry in vector z being 1 is what? What is the probability of that? It means the probability that your data is from the kth cluster. And how much is that? Well, that's pi k. Remember, these pi k's are the proportions of what? The number of data in each cluster divided by the total number. So I can say pi k is the probability that your data is coming from the kth cluster, and that is the same as saying z of k equals what? The kth entry in vector z equals 1. Okay, now if that is the probability for the kth entry in z being 1, I can say the probability for the total vector z is what? Is equal to pi, this is a product, right? The product of k going from 1 to capital K of pi to the k, pi k to the power z to the k, right? Because you know all of these zk's are what? 0 except for one of them, that is 1, right? So if I use, let's say the second cluster is the cluster of label, it's going to be pi 2 to the z2, and z2 is 1. And all of the other pi's, pi 1, pi 3, pi 4, they are all going to be raised to the power what? 0, and power 0, anything to the power 0 is 1. So when you multiply them together, right, it's going to be like pi 1 to the 0 times, let's say, pi 2 to what? To z2, but z2, you know, the second entry should be equal to what? Should be equal to 1, because that data belongs to cluster 2 times what? Times pi 3 to the power 0 all the way dot to what? Dot to pi capital K to, again, power 0. And you know all these power zeros are 1, so it simply is going to be pi 2, and that is exactly what we will have. Okay, so this is basically just writing this in a more fancy way, writing it as a product term and a bunch of power terms. But this guy is going to come handy soon, this kind of fancier formula. So we're going to see it soon here in the next line. So that's why we added this formula here. So now I have written here down for you the conditional probability of observation x given a particular value for z for the class. And here, if it's for zk equal 1, then it's the same as a Gaussian distribution where data x comes from the average mu k and the covariance sigma k with this formula that we had here on the top. Okay, so this is that distribution where you have mu and sigma, and your data x comes from that. So this is for zk equal 1, or in general for the entire z. If you want to write it, then you can write it in a similar manner as you wrote this formula on the top, that you can have all of these normal distributions, raise them to the power zk, and multiply them together. And it is going to be something exactly similar to this top one, because the zk's are all 0 except for one of them, that is 1. And the one that is 1 is the designated class, right? So basically you get something like this one back. Okay, so this is the what we call the likelihood function. The likelihood that the observation x is coming from class z, or in general the variable z here. Now If we want, we can also calculate the total probability of observing any observation xi by summing up over all joint probabilities, right? So when I say joint probability, I mean what? I mean P of xi and z, right? So if I sum over this, over all z, possible values of z, that is going to give me what? P of xi. But how do I find this? Well, I know if I divide this by what? By P of z, that is the definition of P of xi given z, correct? That's the definition of P of xi given z. So from here, if I want this part, this joint probability, all I need is to cross multiply these two terms together, and that's exactly what you have over here. Okay, and what is each one of these terms? Well, your likelihood function P of xi given z, we just calculated on the top. That's a normal distribution, and your P of z, as we calculated earlier, that's pi of k, right? Pi sub k, which we had it up here, right? So here we plug them in, and this is going to be the total probability of observing a single value of x, a single observation x. Now, if you have more than one observation, which you always do, in clustering, you don't have one single data point, you have a ton of data points typically, right? So let's say you put all of these observations x1 to xn into this big giant X, right? And you have n observations in general. So n is the number of observations, and remember k was the number of clusters that you have to provide. N is provided by the data. Now, if these observations are independent from each other, right? So P of xi given xj is the same as P of xi. Xi and xj do not depend on each other. Then you can have each one of these terms, that is the probability of what? The probability of one observation. You can have each one of these guys and multiply them together, right? Because you know, if two things are independent, if P of x1, let's say given x2 is the same as P of x1, so these two are independent. Another way to show it is that P of x1 and x2 is equal to what? P of x1 times P of x2. That's another way to define what? Independence in probabilities. So here I have all of these sigma terms, right? Normal distribution times pi k, which is for each one of the xi's. And then I multiply them together to get what? To get the total probability of all of my observations. Now, of course, these are assuming that I have my set of parameters theta. And what are thetas? Thetas are all of these data that I need for clusters, their proportions, their averages, and their covariance matrices. So this is the function we are after maximizing it, right? This is the function that we try to maximize. Maximize the chance that all of these observations are coming from what? Are coming from these k clusters with these parameters, pi I, mu I, and sigma I. If we choose this theta such that this function becomes maximum, then we chose the right cluster parameters, right? So this theta is really the theta star, the actual values are the argmax of this p function. Now, we typically do not use this function in its original form like this. We use natural log of that. And the reason is natural log converts the product into a summation for me, as you can see over here. And so we maximize the natural log of this likelihood function instead of the function itself, because now I have double summation, and it's much easier to, in optimizations, to work with double summations than with a pi followed by a summation. Okay, so we try to maximize this function by changing these sets of parameters theta, and as I said, maximize this likelihood function, which we call it expectation maximization or maximum likelihood estimation in this case. Okay, that is the goal that we have. Now, before I go more into the mathematical formulas and so on, so let's say here, this is a histogram of some observations. So these are my observations that you can see. This is the histogram of them, right? Or the distribution of them. And what I want to do is to say that this distribution is a linear combination of what? Some Gaussian distributions. Which ones are these? These are this guy, this one, this one, this one, and this guy. So I have 5 Gaussian distributions, each one with its own what? With its own center, with its own sigma, and with its own number of sample points. And if I add these 5 Gaussian distributions together, right, then I get what? I get this underlying distribution that I have in the histogram, this one, right, this guy, which you can see over here. So I want to break down my overall data into a linear combination of what? As we said, a linear combination of some Gaussian functions. These are the coefficients of that linear combination, and these are your Gaussian distributions. And again, the unknowns are pi's, the mu's, and the sigmas. Okay, so this is in general what we need to do. Now, here there is one more thing I need to define, and then we talk about that expectation maximization, right? Or maximizing the likelihood function. How do we do that? So before that, I need to define one extra term for you, and that is called the responsibility of Gaussian component K in explaining observation X, or it's a posterior probability. So far, as you can see, we have calculated P of X given Z, right? It was all P of X given Z. The likelihood that the observation comes from the clusters. Now here, we go and calculate the opposite, which is what? The chance that a cluster exists with the observation that I have. Okay, it's the posterior probability, which we can calculate using the Bayes formula, as you can see here. So what is the chance that Z of K equals 1 if I have all of these observation X's, which I can show it with the function gamma of ZK. And again, based on the Bayes formula, it's going to be P of ZK equal 1 times P of X given ZK equal 1 divided by P of X, right? We all remember the Bayes formula that P of A given B is what? This is equal to P of B given A, right? Times P of A, and then divided by what? P of B. I have explained this in one of my original videos, right? So this is the posterior probability, this is the likelihood function, this is the prior probability, and this is what? This is the normalizing factor, basically. So, so far we have calculated this guy. Now we're going to calculate this one. Okay, and that's what you can see over here. So the denominator is the only term that we need to expand. And remember, this is the probability of observation X, which we can do it by summation over all of the P of Z, J is equal 1 times P of X given that. That's basically what we had over here, this guy, this one. Okay, that's the same as that. So we have it here. We write it as the denominator and we expand it, right? That's integrating over all joint terms, individual joint terms. And now this P of ZK equal 1, based on our notation, this guy is what we called pi k, right? So this one here is your pi k, as you can see. And P of Zj equal 1 is pi j. So we replace them like that. And then these likelihood functions, as we know, these likelihood functions are the Gaussian functions. So we write them as the Gaussian functions. Okay, so this was what? The posterior probability, okay? Or here we call it the responsibility of Gaussian component K in explaining the entire observation. This is gamma of the gamma function of ZK. Just keep that in mind. We need that. So now let's go ahead and try what? Try to find the best theta that maximizes this function here, this function in this dollar equation. We want to what? We want to find the sets of mu, sigma, and pi, or we call it theta, that maximizes this natural log function, okay? If we can find it, that's all we need to do. So how do we do that? So, we know from calculus that if theta, or all of these mu, sigma, and pi, will make that function in the dollar equation maximum, partial derivative of that function with respect to these three parameters, mu, sigma, and pi, ought to be 0. So here we set these three equations here, and then from there we solve for mu, we solve for sigma, and we solve for pi. If we solve for mu, pi, and sigma, we get these relations 1, 3, and 4 here that we'll need, and you can easily show them. So I'm not going to go over derivation of 1, 3, and 4, but you can take derivative from this dollar equation with respect to these parameters here, right? And show that these equations can be derived 1, 3, and 4. Now, in all of these 1, 3, and 4, there is a gamma function of zi and k that you need to what? You need to have, okay? And these guys are those what? Those posterior probabilities, those responsibility terms, okay? So here I have rewritten it for you, that gamma of zi and k that you need here in equation 1, you need it in equation 3, as you can see, and the 4 you don't need it, although in 4 you need to calculate nk, and nk here, we'll talk about it, that also needs what? Gamma of zik. So in order to go through 1, 3, and 4, we need to calculate this important term here, gamma of zi and k, which is just based on the definition I gave above. That's how you calculate what? That's how you calculate this gamma of zi and k, right? Just consider this term here on the top and this term on the bottom, and you exactly see that this is what? This is your gamma zi k, okay? And you use it in all of the formulas, as I said. Now, the next thing that I need to explain in these update equations is this term nk, which is summation over I from I1 to n, summation over all of the observations of gamma zi k. So basically, what is this here? This is the effective number of points assigned to cluster what? To cluster K. Okay, that's why you see I divide that number of data points in cluster K by all of the data points, and that is going to give me proportion of the data in what? In cluster K. Okay, so here I have three update equations, 1, 3, and 4. And in 4, I need two terms in 1, 3, and 4 as well, nk and gamma, which are given by equation what? Equation 2 here. So if we want to summarize the whole process for expectation maximization here, or maximizing that likelihood in the dollar equation, how do we do it? We do it in 2 steps. Step 1, we call it E step, or expectation step, where we initialize the means, the covariances, and the proportion or mixing coefficients, mu's, sigmas, and pi's. We start with some guess, right? And then what? Then using these parameters and all of the observation x's that I have, I evaluate this natural log function that I have in the dollar equation. If you look at it, in order to calculate this, I need to know how many observations I have. I need to have those observations. I need to have my parameters for the distributions, and I need to know the number of distributions or clusters. If I have this with this double summation, I can calculate what? This function that I'm going to maximize, right? So now what? Now I need to change my mu, sigma, and pi in order to reach to the maximum of this function. How am I going to do that? Well, the next step is called the maximization step, and there is another name for it if you want. They call it the M step, right? So we have E step and M step. So what do we do in the M step? Now it is time to apply the equations 1, 3, and 4 to update my values of mu, sigma, and pi. But before I can do that, I need to, in all of them, I need to have these posterior terms, gammas. So first I go to equation 2 and calculate what? The gammas using this formula, this one here, and I calculate the effective number of observations in each cluster, which is being done by summing up over these gamma zik's, right? Once I have that nk I needed in equations 1, 3, and 4. So before I can go to 1, first I need to go to 2, then go to 1, really. And can I calculate this gamma zik with everything I have right now? Yes, because I have my mu's, my sigmas, my pi's, I have my x's, and I know how to create a normal distribution function, which I have it all the way up here, right? This is your normal function here, this guy, right? And then once I have all of those gamma terms or posterior terms calculated from 2 as well as nk, then I go to my equations 1, 3, and 4 and re-evaluate or update my mu's, sigmas, and pi's, and I keep repeating these 2 steps until the algorithm converges. And what does convergence means? Means there is not any meaningful change in mu's, in pi's, and in sigmas. So here you can see a simple demo of this algorithm. So here in picture A, this picture coming from the book by Bishop, in picture A, I have all of my observations in green, and I guess 2 values for mu's and sigmas and pi's in this case. So this is my, let's say, mu1, this is my mu2, these are the locations. The sigmas here, they have the same values and they are diagonal. That's why you see the distributions are like circles. And then the size of them are the same, so it's kind of assuming that each one of them is using a pi of 1/2, pi k of 1/2. Good, so this is, I assume, and you see it's completely irrelevant to my data. My centers, my shape of the distributions are completely off. So now I start what? I start updating. So first I calculate my likelihood function using this data, and let's say it gives me some number. Then I come to equation 2, calculate the gammas, and then using gammas and nk, I calculate my new mu, my new pi, and my new what? My new sigma. But before that, here in B, you can see basically the labeling that is done before I go to C and show you the updates. So what is it that you are seeing in B? In B, you're looking at what? You're looking at the gamma terms here, okay? So some of the data are better explained by this distribution on the top left. Some of the data are better explained by what? By the data on the bottom right, and some of them in the middle can be equally explained by both of the data. So those data for which what? For which the explanations or those gamma terms are larger with this cluster here on the top left, those have a blue color. On the other hand, you have some data that have higher gammas from the cluster on the bottom right, so they have more red color. And then there are some data in between that are kind of equally explained by both of the clusters. Those have a mixture of red and what? Blue, so their colors are purple, as you can see here in the middle, okay? So this is the update of the gammas that you can see in picture B. Now in picture C, now that the gammas are updated, Now you can update, re-update, or re-evaluate your mu's, sigmas, and your pi's, and now clearly those circles, their centers and their shapes are not going to well define these clusters here. So I have to move their centers from wherever it was to somewhere that is kind of more center of the data, right? You see clearly that my previous centers are now shifted, and now these are more kind of, they're closer to being the center of all of these data instead of these off center points. And the shape of the distribution, instead of being a circle, now is elliptic, because that's how the data is spread. It's like an ellipse. So the sigmas are clearly updated, and the mu's are updated, and you see the size of the two circles are, the ellipses are not the same. That means the pi's are updated as well. Then here it's in the first iteration. Then when you go to 2 iterations of E and M, then you can see that now the mu's changed a little bit, the pi's, the sigmas changed a little bit. And then as you go more and more iterations, now you see that the mu's are changing and kind of converging to some fixed locations. Your sigmas are changing, and your proportions are also changing, okay? And to demonstrate that in Matlab, I have written a code. Again, a big portion of it is coming from Matlab help. Okay, and credit goes to the people who wrote the code, but here I simplified it and I added some stuff to it to make it a little bit nicer to understand here. So here I go with 3 clusters of data coming from normal distributions, and I set up my centers in these 3 locations, okay? And these are my sigma matrices, my covariance matrices. They are all diagonal, as you can see. And my proportions, or the number of data, not really proportions, the number of data are 100, 100, and 100. So the proportions are really 1/3 here. Okay, so if you want, instead of proportion 1, I can call it what? I can call it num1, right? And that does make a little bit more sense. Let's not call it that, and let's change this one, and let's change this one. And this way, because when I pass them to this command mvnrand, they need the number of data points, not proportions. So here, what is this command? mvnrand, that's multi-variable normal distribution random numbers. So they generate random numbers from a normal distribution for you. It could be multi-variable, okay? So here you pass to it your mu1 and sigma1 and n1. It generates a bunch of data from the first cluster. Then you do similar thing for the second and the third one, and you concatenate them together. And these are all of your observations. So here I'm artificially creating my observation data instead of creating it from or reading it from an existing file or database. I'm artificially creating that, so I have more control over it. And I can show you that data here, right? So let me go ahead and show you the data. So this is the data that you have in general, and now you're going to what? You're going to say, how can you describe this data for me? With what? With a bunch of normal 2D Gaussian distributions. And the goal is to find their mu, sigmas, and pi's. And here I have to tell it how many clusters I think exist. So here I go with 3. And I ask it to repeat the iterations for 1,000 times maximum for me. Okay. Then here, this is my GMM fitting function, which calculates those 3 parameters and does all the iterations. So it's called fit GM, Gaussian Mixture GM, dist, okay? And then what you need to pass to it is your data and the number of clusters and a bunch of options if you want. But all it really needs is X and K. But what are the options if you want to tell them? One is the covariance type. Is it full or diagonal? The other option you have for here is diagonal. Do you think your covariance matrices are full, which means it has all 4 parameters, or they are diagonal? Here I gave it full, but in my case, you see they're all diagonal. So if I want, I can go ahead and say what? They are diagonal, they are not full. So that means these numbers, when you say full, means these numbers are not generally 0. It can have off-diagonal numbers. Then shared covariance, is this true or false? If it's true, means some of these data have what? The same covariance matrices. In my case, they are not sharing the same covariance matrix, so the answer is false. And then I can have, as I said, 1,000 maximum iterations. So first thing I do, I basically fit my GMM model to my data with the number of clusters. Now I want to what? I want to show you some information and do the plot, something similar to what? Similar to these guys. I want to show you some plot like that, and I want to show you the pi's, mu's, and sigmas that my algorithm has converged to. So I want to show you those. So how do I do that? So when you get this fitted model, right, and here I call it GM fit, there is one field of that called mu. It's a structure, and one field of that is called mu, one field of that is called sigma. Pay attention, this is capital C. And one field of that is called component proportion, where both C and P are capital letter. So the thing you can do is get these numbers out, okay? So if I want to know how much are those numbers calculated by the algorithm, so here are the centers of the clusters. These are the covariance matrices, okay? Now remember, I said diagonal, so it only gives me diagonal numbers of the matrices. And then I have some proportions. And as you can see, the proportions are very close to 1/3, each one of them, right? They're very close to 1/3. And if you look at these locations, do they make any sense? So it says the first one is like -0.76 is -1, right? And if I go to my data, -0.76, -1, that's this one here. This one, it's calculated very accurately. This one, a little bit off. The other locations are 1, 2, and 5, 5. Let's see what this one gave me. This is the 5, 5, and this is the 1, 2. So it's not really bad, given that these clusters have a bunch of overlap with each other, okay? So the 3 clusters are not completely isolated. If they were completely off from each other by giving big distances between their mu's and reducing their sigmas, so they were completely no overlapping, then those numbers would be very accurate. But since there are overlaps, you would never get these guesses to be perfectly equal to your original set of data. And if you look at the diagonal numbers, there are 2, 1, 1, 1, 2, and 1.5. And I assume this is your 2, 1, this is your 2, 1.5, and this is your 1, 1. Okay, again, nothing is going to be perfect, but it's not really bad considering the overlaps that I have. Now, after I do this plot, I'm going to go and change this and separate the clusters, and you see that my guesses are going to be much better. So far, these are what? These are the estimations. The other thing you need to do is get the cluster index. So what is this one? Here, I pass my fitted model and my data and pass it to the command cluster and ask for a cluster index. What is this? Here, it is going to tell you each one of your data observations in X belongs to which cluster. Okay, so when I run this part, which I already did, if I go and look at the cluster index, right here, you see it's 300 by 1. So let's take a look at that cluster index. You see these are only numbers 1, 2, and 3. So that cluster is going to what? Pick one of the 3 clusters. Remember, this method is not going to give you a perfect number like 1, 2, or 3. It is going to assign each data to each cluster using some probabilities. But between those probabilities, one of them is higher and this cluster is really taking that one, and based on that is telling you this data belongs to cluster 1, cluster 2, or cluster 3. Okay, so this is just showing which one of the clusters. This is making a final decision basically based on those probabilities. That's what this one does. And why do I need it? I need it for my gscatter function, which I showed you in one of my previous videos. So here you pass your x data to it and the cluster index. What does it do? It creates a scatter plot, but with different colors. Each class will get a different color, right? So if I go ahead and just show you this part only, you can see that I have a scatter plot with 3 different colors, right? This is cluster 1, this is cluster 2, this is cluster 3, right? And the way I need to do it is by passing it an array or a matrix that has a number for each and every one of the data in X. And that is the job done by gscatter, which you can see clearly here. So this is so far my labeling that is done, right? So if I look at my data, I see 3 separate clusters, and this is how each one of the data belongs to one of the clusters. But what about those ellipses and so on? Can I draw these ellipses or anything like that around my data? Can I do this extra part of the plotting? The answer is yes. I'm going to now what? I'm going to draw these ellipses and circles around those clusters and make this plot a little bit nicer for you. So how do I do that here? First, you generate a bunch of data using the mesh grid command, and you go from the min of x, the first component of x minus 2, the max of the x1 component plus 2 for the horizontal direction. You do a similar thing for vertical direction, 500 data points, pass them to the mesh grid command, and then vectorize them all and call it x naught. So this x naught is a ton of data in the horizontal, vertical, and along the grid points that are all vectorized and concatenated together, called x naught. Then you pass this, all of these data points, x naught, which are way more than the original data. You pass all of them with the fitted model to the function called mahal, and this is the Mahalanobis distance, which I discussed in one of my earlier videos. And this is the distance from a point to a distribution. So instead of like Euclidean distance, that is the distance between one point and another, this is the distance from a point to a distribution. So it takes into account the sigma of that distribution as well as the center of it. Called the Mahalanobis distance, and this is a distance that is used a lot in machine learning. So I get this Mahalanobis distance for all of the data in the mesh grid and call it Mahal distance. And now I use that Mahal distance to what? To basically determine for each and every one of those lots of points that I have generated, 500 times 500 data points, right? For all of them, the distance to these 3 clusters that I have, and see it's closer to which one of these clusters. So I can allocate them to one of these 3 colors, and then I'm not gonna draw an ellipse. I'm gonna form those ellipses by a lot of tiny points. So my ellipses are not gonna be a curve, they are gonna be a surface filled with lots and lots of points. Okay, that's what I'm doing here. So look, I did the scatter plot with color. Then what? At the center of each one of my clusters, at the gmfit.mu of them, data 1 and data 2, I add a black X to the center of each cluster. So here you see now there is a black X added at the center of each one of the clusters. Then I go ahead and from 1 to the maximum number of clusters, which is 3, what do I do? I go ahead and I get the color of the data that I used in that scatter plot. Remember, this scatter plot has three colors, right? It has blue, yellow, and red. I get the color for the label of that scatter plot, and then what? I use that color and the data in the mesh grid, based on their Mahalanobis distance, thresholded, I give them one of the three colors. So I either give them blue or yellow or red, right? And then when I colored all of my data points in the mesh grid, then I'm going to turn off the legend and add a title. So if I do this part for you, or run the whole code actually, then you can see what I exactly mean by those ellipses. So here is my original data. Here are the three clusters. And as you can see here, those ellipses are not like drawn or something by lines. They are formed by lots and lots of what? Small points here. So this is just like another scatter plot. Okay, so this is the ellipse that you can kind of fit to your third cluster. This is for second cluster. This is for what? This is for your first cluster. Okay, or you could draw ellipses using these numbers that you have, using these centers and these covariance matrices. If you want, you can use a command to draw an ellipse for you, where those two are the major directions, right? The eigenvalues and eigenvectors of those matrices, of those covariance matrices, determine the amount of rotation of it and the major and minor axes, right? And then these guys you can use to change the size of those ellipses, and these to determine what the center of the ellipses. So if you want, you can approach this in a different way. But here I'm kind of following what Matlab help did, right? But if you want, you can create these ellipses in a separate way. Now, as I told you before I stop this video, I would like to, because remember these estimates are not perfect or nowhere super close to these. I mean, they are not bad, some of them, but not very close. So here I'm gonna get these clusters a little bit off from each other, right? So this -1 and 1, I make it like -3 and -4, and that guy, I make it like 5 and 7. So shift them from each other. Let's see now if I can get some better data. If I have three completely isolated clusters, now you see that my clusters are relatively separated, and you can see them here too. And now if I go and look at my numbers, okay, first of all, as you can see, the proportions are really 1/3 each. And if you look here, this number is almost 1 and 2. This number is -3, -4, and this guy is almost 4 and 5 and 7. And I assume these are these numbers. So you see, they are very good here, right? And I can separate them further, like I can make this 6 and 8 and something like that. And then my estimates are going to be even better, right? So the further overlay or overlap you have between your clusters, the further your estimates are going to be from your simulated, the numbers that you used in simulations and generating these numbers. But clearly you can see that now you have three separate clusters, and you see the proportions are right. And this is -3, -4, that is 6 and 8, and this is 1 and 2, right? Very close. And your sigmas are not too bad either, okay? Now your sigmas are typically the least accurate thing. Your proportions are the closest thing to the real life numbers that you used here, and your mu's are the next best thing, okay? Typically in calculations of covariance values, the accuracy is not as good as the proportions and the means, okay, because of the quadratic nature of the covariances. But you clearly see that the algorithm works and it gives me the clusters. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.